Hey guys, so I'm going to show another example of these push away problems. But in this one, we're not going to have numbers. We're going to solve this with letters. It's a literal problem. So here we have two scalars of masses m and 1.3 m. Those are the masses that are at rest. And this is what I mean by literal. There's no numbers. So instead of having something like 100, you're just going to have m. If you had 100, 1.3 m would have meant 130. But we don't have masses. But that's fine. We can solve with this. So we're just going to plug those in instead. When they push against each other for t seconds, so they do this for an amount of time, delta t equals big T, the lighter moves back with a speed of v. Let's draw this real quick. So pushing against each other, pretend these are people, and they're pushing against each other. Now the problem doesn't say who's left or right, so I'm going to put m here, 1.3 here. Just doesn't matter the direction, the arrangement. And now they're going to push, and then this guy is going to go back this way with the speed of v. Now, this is after the events, after they push on each other. So this is v, let's call it 1, v1 final. Let's call this guy 2. This v1 final is big V. And because it's to the left, I'm going to add a negative here. Now, had I drawn them differently, it would have been, if m was here, it would have been going to the right. So it would have been positive v. The second mass, v2 final, has unknown velocity after the push, and that's what we want to know. What is the speed of the heavier skater? We want to derive an expression, which means instead of a number, we're going to have some letters, m's and v's. Okay, and the way we're going to do this is by using conservation of momentum, since this is a push-away problem. So I'm going to write this equation here real quick. m1 v1 m2 v2 initial, m1 v1, m2 v2 final. Next thing I'm going to do is replace the masses m1 and m2 with these masses here. So big M, and I'm going to leave spaces for the velocities. Forgot a little m here, or a big M rather. All right, so now let's put the velocities. The initial velocity here is 0 for both of these guys, because initially they're just looking at each other at rest. So there's no initial velocity. The final velocity, however, of the first one is right here. It goes to the left with negative v. And the second one, we don't know, so I'm going to put v2 final, and that's actually what we want to know. We want to calculate that, or derive an expression for it. Okay, this whole thing here becomes 0. And now we're going to move everything out of the way so that v2 final is by itself. It means that this goes to the other side as a positive, and this goes to the other side dividing. Cool. Notice that the masses cancel, and you're left with the final answer, which is that v2 final equals big V over 1.3. The answer was supposed to be meters per second. The answer was supposed to be in terms of m and v. It doesn't mean that all the variables have to show up. It just means that no variables other than these could show up. So this should make sense because the heavier object, this is the heavier object, ended up being slower by the same factor. So it's heavier by a factor of 1.3. It ended up being slower by a factor of 1.3. And that should make sense. All right, so part B is a little bit more tricky. We want to know what is the average force. Now here, I hope the word average kind of give you a hint that you should be using impulse. Remember, impulse, J is force, average, time, delta T, equals the change in momentum. Now remember, change in momentum means P final minus P initial. In this particular problem, there is no momentum initial because the two objects aren't moving, right? They're initially at rest. Now, the two of them are pushing each other with the same force. You can think of this as F1 and F2, but they're really the same magnitude. So I can just think of it as F, okay, F. Now, they are pushing on each other, and what makes this confusing is you have to look at a single object to be able to do this. So what we're going to do is we're going to say impulse on object 1, on 1, We're going to go with 1 because 1 has the simplest mass, the simpler mass, just m instead of 1.3 m. So the impulse on 1 is the force on 1, delta t, and it is the final momentum of 1. So the force on you gives the impulse of you, gives your impulse, okay? I'm looking for this. So the force on object 1, the time is big T, and this is going to be m. Since it's 1, it's going to be m1 v1 final. Now let's replace these numbers. F on 1. The mass of 1 is big M. The final velocity is negative big V. And we divide everything by T. So the force applied on the first object is negative mv over t. Now, that's the final answer. Negative is because it is to the left. We probably just want the magnitude. So let's just say the magnitude of the force average of them on each other is mv over t. Okay? Either one is fine. This guy here gets pushed this way with a positive force, right? So it'd be positive mv over t. That's it. Cool. So it's a little bit tricky, a little bit unusual, but I wanted to do this one so you guys know how to do it. All right, that's it.